differentiation of sine x and cos x from first principles. So y equals sine x, so dy by dx, the correct notation, is cos x. So that's what you get when you differentiate sine. Pretty straightforward. In function notation, f dash x is equal to cos x. Now sometimes you don't have y equals and you don't have function notation either. You might just have a single term or an expression and you have to differentiate. In that case we use this notation, d by dx. d by dx is a differential operator. It tells you to differentiate whatever comes next. So if you differentiate sine x, you get cos x. And we're not using y equals or function notation either here. Now we're going to show from first principles that if you differentiate sine you get cos, and if you differentiate cos you get minus sine. Okay, this graph is not sine or cos, it's just to generalize and show you where differentiation from first principles comes from. So all I have is a curve, and what I'm looking for is the gradient here, right there. Now I could draw a tangent to the curve, then the gradient of the tangent and the curve would be the same, something like this. I need 2 points on the line to work out the gradient, but I only have 1 point here, so you can't work out the gradient using the tangent. So instead we use 2 points on the curve and draw a line between them called a chord, and then we bring this point here, the yellow one, closer and closer to the one in green, the one that we're interested in. So this chord starts getting smaller like this, and what we're doing is we're making h, which is the distance here, this, we're making that smaller and smaller until h is approaching 0. It's so small. At that point the gradient of the chord and the gradient of the curve at that point should be the same. So you will have seen this already somewhere, the formula that we use for differentiation from first principles, and all it's saying is in the numerator it says the change in y, in the denominator it says the change in x, change in y over change in x, and we make h really small. The graph of y equals sine x, I want to work out the gradient right here. I choose a second point on my curve. Along the x direction, my second point is the distance h away from the first point. So if this has a coordinate x, this will be x plus h. And then the y coordinates, well, you just get them from the equation here, y equals. So this is going to be sine of the x coordinate for that point, which is just x, and this is going to be the sine of the x coordinate for this point, which is x plus h. So you have that x coordinate with that y coordinate, and this x coordinate with this y coordinate. Now we just need to do the change in y over the change in x, and here is a chord joining my 2 points. So I'm going to move this point, the green one, closer and closer to the original point. So the gradient of the chord, change in y over change in x. And then I need to make h really small, which means the 2 points are really, really close together. Now I need to expand this. Here are the addition angle formulae, the identities, and we're going to use this one. So we get this. I'm going to take sine x out from these two terms. I'm going to put them together and factorize out the sine x to get this. And you can see that if you multiply these two, you get that term, multiply these two, you get that term, and this was already here. Now remember, on the graph along here in the x direction we have angles, and as this point comes really, really close to this point, then the angle here, the difference between the angles, is extremely small. H is extremely small. Okay, so I can use a small angle approximation for sine h and cos h, like this. So if I replace the cos h with 1 minus h squared over 2, and replace sine h with h, we get these. We can simplify, the ones will cancel, and then we've got this, because the h from there and there will cancel, and remember cos x and that h are separate. Okay, so they do cancel, and then I can cancel the h from here and one from here, and we know that h tends to 0, so this term is 0 times sine x is 0. We're just left with cos x, and that's the proof from first principles that if you differentiate sine you get cos, and the proof is done in radians for us to use the small angle approximations. Now if I start with the graph of the cosine of x instead and do the exact same thing as I did with sine x, change in y over change in x, and then make h really small, I will get this, and then I need to expand this using the addition angle identities for cosine, and we'll get these terms, and then factorize. There's a cosine term here, cos x term I should say, and there's a cos x term there, so if I put that on the outside here, and you can see that if I multiply the brackets out I will get that term, and if I multiply these two I will get that term. That term is here. And for small angles, because h is really small, because our 2 points on the graph where there's a chord drawn between them are so close together, and the difference in their x coordinates is equal to h, and that's a very small angle, we can use the small angle approximations. So we get terms that we can simplify like this, and then we know that h is approaching 0, so this term becomes 0 times cos x is 0. We're just left with the minus sine x. So if you differentiate cos x you get minus sine x, and it's all done in radians. So if angles are given in degrees and you're differentiating trig functions, convert to radians first.